All right. Welcome back. We seem to have made some progress on the people sitting in the hallway front here, so I guess that's good. I'll talk a little bit about the wait list later. So we're going to start 162 by giving you a little bit of history, which, the best thing about history is you can see some of the interesting things that happened and maybe laugh sometimes, maybe not repeat history. That's always a good thing. So just before we do that, though, let's do our standard format for class. So last time we, in addition to introducing you to the class, talked a bit about virtual machines. And we're going to view operating systems as kind of a virtual machine abstraction throughout this class. And as you recall, the idea is to take the hardware interface, the physical interface, and turn it into something that's easier to program, more secure, has better overall properties like reliability and dependability and so on. And that's basically what we do in this class. Okay? And it's figuring out what the right layers are to put in here to get from hardware to something interesting. And so we talked a lot about this is a software engineering problem. It's basically turning hardware that's buggy or flaky or doesn't quite do what you want into the ideal perfect virtual hardware. It's optimizing for convenience and utility and security, et cetera. And pretty much for any area in operating systems, and actually in computer science, you can kind of ask yourself, what's the hardware interface and what is the operating system's interface? Now, were there any questions on that sort of, it's a pretty high-level view, but did anybody have any questions from last time? Okay. Now, the other thing that we were doing at the very end, which we're going to finish up since it was kind of a thought, was giving you an example of the kind of thing that the operating system might do. So what the example was we have two processes. You have no idea exactly what a process is. I'll tell you later. But two things that are running at the same time on the piece of hardware, and what we want to do is we want to protect them from each other and protect the operating system from them. And to do that, we have some mechanisms which we're going to introduce, and we're going to put some policies on top of it, okay, on top of those mechanisms. And so basically the goal was prevent user programs from crashing the operating system, prevent them from crashing each other, and later at the end of the lecture, I'll even show you how we could use these same mechanisms to prevent parts of the OS from crashing other parts of the OS. So basically the mechanisms are address translation and dual mode operation. Now, we didn't talk about dual mode operation, which I'm going to want to do, but let's remember exactly what address translation was in a second. The policy we're going to enforce is basically that programs are not allowed to read or write any of the memory of other programs. Okay? Very simple starting idea. And so address translation virtualizes the addresses that the process sees. Okay? So basically, it's got a set of addresses, 0 through 2 to the 32nd or whatever. It thinks it's reading and writing from those addresses, but because of address translation, it turns out that those are actually virtual addresses. The physical underlying addresses are different. Okay? Simple. We're going to put it through a translation table. And we're going to do it with hardware that's efficient enough to be fast, and we'll talk a lot about that later in the term. But you can think of this as there's a CPU, it's executing stuff. The addresses go through a translation box. So this is MAGIC. MAGIC memory unit, actually memory management unit. And then it produces a physical address that goes to the actual DRAM. Okay? And this is a conceptual view of that where here, program 1 has its address space, and what I'm showing you here is kind of a set of things, code, data, heap, stack, etc. These are all words that hopefully you remember from 61C. But, and the addresses kind of go from maybe 0 on up through somewhere in there, and those addresses get translated to actual physical places in DRAM. So when we're in the code segment here, those addresses, which might be from 0 to some point, 3F or 3FF, whatever, get translated to this part of the DRAM. And this code space is translated to this part of the DRAM. Okay? And the thing that you should get from the diagram at this particular point in time is that the set of addresses that are translated to in the physical space don't overlap. Very simple idea, right? If they don't overlap, there's no way, even in principle, for somebody, this program, to read or write this program space, and therefore it can't screw it up, at least in that sense. Okay? Yes?
The diagram seems to suggest that the program sees less of the memory, like a smaller portion of it. Is that true? Or does it think it's getting all of the...
Well, the question of how many addresses there are over here relative to physical ones is actually extremely interesting, and we'll talk a lot about that later. I will say no comment at the moment, so it could be more, it could be less, it could be the same. I think I've got all those covered. But humor aside, the addresses that it has access to here, it thinks it has 100% access to. Okay? Good question. Anybody else? So, no, yeah, go ahead, sorry.
Are we also going to talk about segments in this class?
Yeah. Yeah, we'll talk about segments. You'll love segments. Or not. Question, yeah.
Are we kind of just hoping that we're never running so many processes that we use all our physical memory?
Well, yeah, so that's a great question. So are we hoping that we're using all of, not putting so many processes in here that we overload the memory? In your simple view of things I've given you here, yeah, we better not. In a better view or a more complex view, we start swapping some of this out to disk, and then it's, the total memory we could use is as big as the disk. Or this is kind of a joke, but we could swap it out to tape, and then the total view is as big as the tape, whatever. But yeah, so from this view that I've given you so far, that's right. We can't have more total than there is DRAM. Good. Anybody else? So this is fine and dandy, but there's a bit of a problem with this. Can anybody see what the problem might be? What's the vulnerability of this particular scheme? Yes?
Two different processes might have the virtual address map at the same display.
Let's assume we don't screw that up. So there's never the mapping to the same address. But yeah, a bug in the operating system, that's definitely a vulnerability. What part of this kind of could screw up the protection here? Yeah?
Say a program terminates and we don't properly clean the physical memory,
Okay.
and then another program boots up and it gets mapped to those things. What happens if it's not to the junk data?
Okay, so that's an extremely good, subtle bug. I'm looking for something. We'll actually talk about that when we get to security later. But that's good. That's not quite what I was looking for. Yeah. Okay, so you guys are thinking way in outer space here for now. This is great. That's great. That's a good. I'm looking at the following. What if the translation map is writable by the process? Okay. You guys are very sophisticated today, but I'm thinking simple here. Okay. What happens if this guy can change its mappings? Okay, doesn't that seem like that's a problem? Okay, so the simple problem I'm talking about here is that mapping needs to somehow be out of the realm of changeable by the process, or we've not really done anything from a security standpoint. Okay, there was another question somewhere? No? Okay. Does everybody see that problem? Yeah.
Does the OS have control over the mapping?
Well, since the only entities we've talked about are user programs in the OS, I guess it's got to be the OS that has control. Okay, now that's an interesting question later, but for now the OS, yes. So what do we need to do? We need to somehow restrict the little blue bubble things here, which I haven't told you what they are, so that only the OS can mess with them, not the process. Okay? And so that's why there's this second mechanism called dual mode, which I'm going to tell you about in a second, and then we're going to dive into some history. And we'll actually show you some operating system structures so you go away feeling like you learned something about operating systems today. And some organizations. Okay? So the other half, dual mode protection. So I will submit to you guys that to make that little mapping scheme work, it is the case that the mapping part better be under control of something more secure than just the user level processor. We really haven't fixed anything. Okay? And that's where this dual mode idea comes into play. And the idea is that most hardware today that runs a modern operating system on it, not all of it, but most hardware has at least two modes of operation, one which I'll call user mode, one which I'll call kernel mode. Now, actually, it turns out, does anybody know how many modes, for instance, an x86 processor has? 4. Okay, so there's actually 4 rings. Well, that was one of my TAs. Okay. Okay, so you actually need at least 2. You could have more or less, right? So, but we have at least 2, and the idea is that we're going to have some hardware be restricted to only operating in kernel mode, and the other hardware only operating, or the rest of the hardware operating in user mode. Okay? And so the thing operating in kernel mode is going to be the translation hardware. You know, the memory management unit will only be writable by the kernel. And the way this actually works is that some instructions or operations are prohibited in user mode and only available in kernel mode. And if the user mode process tries to change those things, like change the mapping, we'll get some sort of exception, you know, and then game over, page fault, your program's dead, you know, you lose. So the problem, of course, is if you're running in user mode, how do you ever get back into kernel mode? Everybody see that? I'm running in user mode. I don't have access to any of those instructions. I got to get to kernel mode somehow. And that's actually where the system call architecture comes into play, which is here's a user process. Now notice what this diagram, this is directly from your book, is very simple. Up top here are things running in user mode, and the bottom are things running in kernel mode. And the way we get from user mode to kernel mode is we actually make a run a special instruction that causes a trap. And again, we'll talk more about this later. And that trap turns on kernel mode, and it starts executing at a very well-defined place in the kernel. So you can't just turn on kernel mode, because then that defeats the purpose again, right? Programs run along, turn on kernel mode, screw everything up. Instead, the system call traps into the kernel, turns on kernel mode, and goes to a specific spot, and now we have good code modifies. Okay? Can somebody explain to me why this direction is not something that's hard to imagine? Going from kernel back to user? Yeah. Okay, because the kernel's already scheduling. From a privilege standpoint, what are we doing? Yeah.
Because once you're done with your kernel code, all you have to do is set the mode bit to 0.
Yeah, so basically, the way to look at this is we're removing privileges going this direction. So the kernel, it's easy for the kernel to remove privileges. It's really about gaining privileges that we want to be careful about. And I talk about a mode bit. Any processor that's got at least 2 levels has some bit in some register that says, is it in kernel mode or user mode? And putting yourself into kernel mode is the part we have to be under control, and going back to user mode is not so much. Okay? So that's 2-level dual mode. Okay? And basically that's the second mechanism. We said address translation and dual mode operation are really required somehow to allow us to do memory protection well. Okay, question, yes?
So in order for the first transition to happen, the kernel has to, if the kernel is going to preempt a program, right, the kernel will put the processor back into kernel mode, right?
Yep. So now you're using words preempt, which we haven't talked about, but let's suppose that at some point we want to stop this user process from running. We have to somehow stop it and get back into kernel mode. And there's usually a timer interrupt that'll go off that'll do that for us.
Well, I was going to ask, so how does the processor, quote, know that the kernel is
Oh, again, what'll happen is in the case of the kernel taking control every time period, what actually happens is there's a timer, which is a hardware timer, causes a hardware interrupt, which comes in on a special physical line. Again, it traps into a well-defined part of the kernel. So it isn't that the kernel or that some random code's requesting that transition, but rather what's happening is a hardware element has been told that when it or has been set up so that when it goes off, you go into the kernel. Okay, so much more controlled in that sense. And of course, only the kernel can set that up to happen. Okay, good. So I don't want to belabor this point now because we'll talk about this in detail later, but this is a basic idea, right? We have a set of mechanisms, and with them, we can somehow enforce this policy of protecting memory by not letting any memory overlap. Now, of course, that particular policy is going to be too limited for later because we're going to really want sometimes things to overlap. Okay. And here, by the way, is a standard Unix or Linux system structure where things that run in kernel mode are a whole bunch of stuff like the I/O system, the file system, things that handle swapping. We'll talk about that later. Scheduling, which decides which things get to run where. Virtual memory, all of that stuff runs at kernel mode. And then on top of that, it's a bunch of stuff in user mode like the standard libraries, your applications, and so on. Okay? Fairly standard structure. Now, notice, by the way, that all of this stuff that's running in here is not really protected from itself. So if some part of the kernel over here has a bug, it can screw up another part of the kernel. So what we've just seen here is some sort of monolithic structure for kernels, which we'll talk about a little bit later as to whether that's good or bad. Okay. So Moore's law, again, we talked about it last time, is an interesting little thing that's helping drive change, right? And so it's kind of interesting is I thought I'd put together a table here just so you guys can appreciate this. So 1981, we might have a 10 megahertz CPU, and it might actually take 3 to 10 instructions, or 3 to 10 cycles per instruction to execute. Okay, so that's not very fast. We might have 128 kilobytes of memory. We might have 10 megabytes of disk. I remember a guy I was working for was so excited because he got a 10 megabyte hard disk drive. That was a big deal. Network bandwidth, 9600 baud. Okay, that's 9600 bits per second. Okay, number of address bits might be a 16-bit address space if you're sophisticated. You might have tens of users per machine. And the price might be $25,000. Okay, so this gets you through what, half a year of school? I don't know, maybe more. So what about 2010? Well, I went to a vendor's website. I won't say which one today. And you can get a quad-core processor running at 3 gigahertz which also has, say, a quarter to a half of a cycle per instruction. Why? Because many things are going on at once. So that's a factor of about 1,200 in clock speed, performance ratio, and about 6 to 40 in number of instructions you can get in a cycle. So that's pretty good. DRAM capacity, yeah, let's put in 8 gigabytes, but this is kind of the medium end. That's a factor of 65,000. Let's just put in a little 2 terabyte drive. Normally, by the way, I would spec out a RAID system with 3 or 4 2 terabyte drives in it, at least for my desktop machines. But okay, that's about 200,000 difference. Bandwidth, low-end machines now all have gigabit per second Ethernet. You can get 10 gigabit if you've got the right infrastructure. That's a little faster. Obviously, a 64-bit machine. Factor 4. Less than one user per machine. Why is that? Well, because your machine sits idle a lot of the time, right? Unless you're one of these people that are doing something like SETI at home or something, where when you're not there, it's busy finding aliens for you. Anybody ever run SETI at home? Yeah, it's kind of fun. So that's interesting. The number of users per machine have gone way down. What's the price? Well, I've stuck to 4K just for the heck of it. That's a little cheaper. Okay, so Moore's law is a pretty amazing driver. Okay, and hopefully operating systems have done something interesting over time, okay, to meet this change. So there's nothing like Moore's Law in any other area of business. So I like to think of this. So transportation in 200 years, we went from horseback at 10 mile per hour to the Concorde, which you can't buy or you can't get anymore, but say at 1,000 miles per hour. And I'm ignoring, F-18s because that's not really a normal person's mode of travel. The computers do this level of change every decade, at least up until 2002. Imagine that you had a car that had improved as much over that time as computers had, right? You would be actually running into speed of light problems, probably. Except in the Bay Area where you'd be sitting all the time anyway. So what does this mean for us? It means that techniques have to vary over time. So we're going to study history, we're going to learn from history, but what's kind of interesting is that the way that operating systems were defined and designed actually changed over time because the technology was changing so much. And I place a lot of emphasis on principles in this class, ways of thinking, ways of structuring, rather than specific solutions to specific problems at a specific point in time. Why? Because the technology is going to change out from under you. Okay, so it's much better to learn principles in this class than to learn that when you have a 3 gigahertz processor with 4 cores, you want to do a data structure in this way. Okay, that's probably limited knowledge. Okay, so here is one of the first computers, ENIAC. I love this quote. This machine designed by Eckert and Mauchly was a monstrosity. When it was finished, the ENIAC filled an entire room, weighed 30 tons, and consumed 200 kilowatts of power. Okay, imagine carrying that on the bus. Now, does anybody know what it was for? Yeah.
Artillery trajectory.
Yes. So it turned out that this was right around the entrance of middle of World War II, and what they designed this for was to figure out how to fire shells, and the trajectories were actually very complicated. This machine was not a General von Neumann style machine. To program it, you actually had, here's the programmer, and what he's doing is he's patching cables, okay, to make this thing work. So history phase 1, so we'll start at that far end. Basically, hardware was expensive and humans were cheap. Okay? Here, look at this guy. He's programming, I hate to even call it in binary, he's programming in patch cord. Okay? But that's okay because the machine is expensive. So what you're going to optimize in this regime is more efficient use of the hardware. Okay? Lack of interaction between the user and the computer is okay. So we have a user at a console, maybe, or at a patch board, one user at a time. We're going to have some sort of batch mode where the idea is you load the program, run it, print the results, load the next program, run it, print the results, and so on. Sometime in this range here, the punch card became very popular, and what you'd do is you'd punch your program on a bunch of cards, and then you'd walk down to the machine room and you'd hand your stack of cards to the operator, and he'd put it in the pile, and sometime that night your cards would get loaded, your program would run, you'd get your result the next day, assuming you didn't make a typo in your cards, in which case you had to submit it the next day. Okay, so that's a little bit different interaction. That's a little different way of bowing to the machine, right? So this is optimized clearly for better use of hardware. Basically, if the user is thinking while the machine is idle, that's a big waste. Okay, so you want to feed the computer batches of things, make it always run, and make the users wait. Much better mode. Fortunately, we've gotten out of that mode over time. But the autograder for this course is actually batch operated, so you're going to submit your, here's a project, give me back my results sort of thing, and you'll get your answer back a few hours later. Okay, so you get to experience this and think about what the right way to deal with it is. No protection. So what happens if the batch program has a bug? Well, you might bring the whole machine down. Okay, and you don't want to be known as the person who brought your multi-zillion-dollar machine down with a typo in your punch card. Okay, clearly it happened though. So one of the historical things, core memories. So this is probably only in the brief mists of legend as far as you guys are concerned, but this is how memory storage used to look. And notice there's actually a bunch of little cores. They're little donut-shaped lifesavers that store data, and then you have a bunch of wires crossed in them, and they actually had humans wove these memory planes. Okay, so there was actually a human with a needle that made these things. And basically, each one of these is a bit. Okay, and if the field is going one way, it's a 1, and the other way, it's a 0. And so the term, if you're ever wondering what it meant to dump core, that's literally because memory was core memory, and so dumping core was taking the contents of memory and dumping it out somewhere so you could look at it. Okay? There's actually a fun history of core memory that you could take a look at that link. Okay, any questions? So you can imagine that we're talking about boards with memory that have kilobits on them. Okay, kilobits. So phase 1.5, I would say, is when the computers started becoming really sophisticated. And what's interesting about this is they started optimizing for I/O. Okay, it's easy to think of, I'm going to make sure the machine's always busy. But the question is busy the right use of the machine? So it's possible that if you have something like a disk drive and you submit a job, while it's asking the disk drive to do something, the processor is idle. So that seems like a big waste of your machine. So the first and most important optimization you wanted to do back then was make sure that I/O and computation were overlapped, so that when you're doing I/O, something else is computing. And that was the original reason for doing multitasking, was so that you could have computing going on at the same time as the disk or the other I/O devices. Okay? And so multi-programming was ultimately several programs running simultaneously. Small jobs maybe weren't delayed by large jobs now, because if you have a really large job that lasts for a week and a small job that lasts for an hour, those two can be multiplexed in a way that the short job gets done much quicker than a week. Okay? And we'll talk a lot about scheduling in a couple of weeks. Okay? So scheduling is a big issue here. Now, complexity, unfortunately, gets out of hand. And this is kind of amusing. It's sort of operating systems designers were like kids in a candy store with a new toy. It's like, okay, we're going to optimize for everything we can by making the operating system more complicated. And the kind of primordial example of this is Multics, which was a project at MIT, was announced in 1963 and ran in 1969. So it took them 6 years to go from conception to running. And this basically had the kitchen sink of operating systems ideas in it. Okay, this was amazing, and it was actually part of a real product. Okay, so they did collaboration. If you look at some of the websites about Multics, you'll find that they claim that by the end there was about 1,700 programmers involved in the operating system. Okay, now you can imagine that it's a little hard to have 1,700 programmers give you a stable system. There is a good example of when, yeah, go ahead.
When you say programs run simultaneously, you don't actually mean that at any given moment more than one program is running. If it's multi-threaded.
So what do I actually mean by simultaneous? So in this particular instance, we're going to be mostly talking about concurrent at the beginning, which is the two threads or two things that are running alternate, but only one has actually got the CPU at a time. It's a good question. Later, of course, obviously multi-core is the future, and so that multiple things alternating becomes many things running at the same time. But for now, let's assume that I really mean concurrent rather than parallel. It's a good question. So there's actually, I put a link up for you on the lecture page. You guys should take a look at this rather fun lecture that was by Fernando Corbato from MIT. He got the Turing Award back in, I forget exactly when it was. But his title of his talk was On Building Systems That Fail. And what's interesting about this talk is he talks about how complexity got out of hand in Multics to the point that they couldn't find all the bugs. And why? Okay, why that happened. There's another kind of operating system that's very similar in time to Multics OS 360 was released. This is IBM's operating system, was released with 1,000 known bugs, okay, or APARs is IBM speak for anomalous program activity reports, which, so we're going to release this brand new operating system and it's got 1,000 APARs. Okay, I guess sounds better than anomalous program activity reports. So basically, operating systems finally became a science here because if you didn't turn it into a science, the complexity killed you. Okay? And we're, by the way, going to use Multics as our gold standard of interesting concepts and mechanisms because it really was kind of the forefront of a lot of stuff that ends up in modern operating systems. So I don't want to trash Multics too much. It was a pretty ambitious and amazing project. It just ended up being extremely complicated to the point that Unix actually was really about simplifying Multics to get a system that was stable. Okay, any questions? All right. So here's a picture of a Multics system, about 1976. And I like this quote. We usually ran the machine with the doors open so the operators could see the AQ register display, which gave you an idea of the machine load, and for convenience access to the execute button, which the operator would push to enter the basic operating system if the machine crashed. So basically, they kept the door open so they could see when it crashed, and then they basically hit the MIT equivalent of Control-Alt-Delete on a regular basis. Okay? So the last thing we'll talk about before we talk about administrivia is disks. So I love these early pictures of disk drives. So for instance, I don't know if this is like a Ferrari where you have the person sitting by this screaming 140 megabyte machine. This thing looks like a washing machine, but this is 140 megabytes. All right, and the disks in this, or disk packs, they're these huge platters that were, 8 to 12 inches large, and they were stacked together, and they were put in a case that you could pick up with a handle. Okay, and you'd insert it into literally something that looked like a washing machine, and you'd get your 140 megabytes. Okay, and these things were so huge, and the arms were so powerful that I actually talked to somebody who used to deal with some of these systems, and he said that occasionally they would have races with these disk drives because what they do is they'd program the arms to shake it in the right way, and you'd see which one could walk his disk drive faster. So the thing I want to, other than the size here, to point out to you is notice that in 1973 we were getting about 1.7 megabits per square inch on the disk drive. Okay, so square inch, 1.7 megabits. 1979, it's about 7.7 megabits per square inch. Does anybody know what the going density is? How much? 4. Very good. Looking at my slides, are you? So, so here's a pretty modern disk drive from Seagate. It's got about 400 gigabytes per square inch. Gigabits, excuse me. That should be a little b. It's a 3.5-inch disk, and it's got 4 platters all inside of a little container. And I actually went to the Seagate website, and apparently they're announcing, and I'm sure everybody else is announcing, that they'll have 3 terabyte drives this year. Okay, so the march goes on. Now, the problem with a 3 terabyte drive is if it crashes, you just lost 3 terabytes of data, which is it's enough to make your heart stop. But anyway, details. All right. Questions about disk drives? So as you can see, we've made a little progress. Okay, so let's do some administrivia. Wait list. Well, we've made some progress, although suddenly we're full again here. Basically, as far as I know, all seniors that are in the major should actually be in the class now. If this is not true, you should let me know. Okay? That unfortunately leaves the juniors, a few grad students, and a couple of non-major seniors. I don't know what to tell you. So we did lose a couple of people dropped, but I don't know. We'll see what happens over the weekend. Maybe if I make this a really boring lecture, we'll have space for the rest of you guys. Anyway, let me know if my first statement here is false, because I think everybody who's a senior in the major should be in now. Okay. Who didn't get an account form last time? Okay, a few of you. I apologize for that. I have extra ones. Make sure to stop by the front here when the class is over, so you can get one. How many people who got a form have logged in yet, or already? Good. So those of you who A, got a form but B, didn't log in, bad students. Okay, you should log in soon. Make sure there isn't any problem, because every now and then we have some account has a weird problem, something to do with the Twilight Zone, I think. Yes?
So I logged in yesterday and noticed I couldn't get the register script going. What's up with that?
Okay, well, you're one of those people that are in the Twilight Zone. I don't know what's going on with the register script.
I emailed Inst and they just switched to Bash, and so they fixed the login time. Now, if you log in again, it'll run.
Okay, so if you log in again, it'll be fixed. So incidentally, the reason I have everybody log in right away is because there's always some weird thing that happens every term. I've never had a term where there weren't weird bugs, and so I'm sorry if you encountered them. But definitely try to log in. Make sure you've got all your resources. Don't quite have the Nacho Reader done yet, but we will soon. It will be early next week. It'll be available down at Copy Central, Hearst and Euclid. You can check out the new Northside Cafe, which has some very good sandwiches. Anybody been to the Northside Cafe? Yeah, nice. Yeah, okay. That was a little plug. I get my payment later with a sandwich. We've also seemed to successfully have captured the first lecture. So I only updated it this afternoon, but the way this goes is if you look at the lecture page, couple of days after the lecture, the link of the title of the lecture actually is an MP4 file, and if it turns out that you've installed Apple QuickTime, you can play it. Now, if you don't want to install Apple QuickTime, you can do something that's a few more clicks, which is right at the top of the lecture page is a link that says Videocast here. If you click on that, all the lectures are given, and there's both audio and video, and you click on the little picture of a video, and it pops up a player for you without you installing QuickTime. So it's web only. So hopefully we'll be lucky. We've had previous terms, we've had some dropouts where every now and then a lecture wouldn't get recorded in video for reasons that's, I think, a mystery to everybody. But hopefully that won't happen. Don't forget, we're not quite into first project yet, but no slip days on the first phase of the projects. The slip days are only on the code. And finally, this course is 100% in Java. So if you're not comfortable with Java, you better get comfortable soon. I've had people who tried to be not comfortable with Java, and they didn't do too well. Okay, so if you haven't taken 61B so that you're a super Java programmer, you might want to consider like a self-paced course or something, or get yourself a Java book and start, I don't know, programming something interesting or something to get yourself up to speed. So I would do that now. Okay? I'm assuming everybody here probably isn't in the mode of not being Java people, but never know. Okay, any questions? Yes? You know what, the things I gave you actually are instructional login accounts, and they'll let you log in at in the labs on the second floor. You can also forward your email if you want from them by setting up a .forward file on the instructional machines. But they're actual accounts, they got storage, etc. You'll need to have the account to actually do your submissions and stuff at minimum. Okay. It's it's Unix, a variant, some sort on, I don't remember what's on Cori right now. I think it's some form of Linux, but I'm not entirely sure. Solaris. Oh, it's still Solaris. Okay. So it's a variant of Unix. time to start thinking about groups. So here's what's going to happen. Next Tuesday, that's a week from yesterday, you're going to have to submit your group by saying which sections you can attend. And so that means you should figure out what groups you're in. Now, basically, we're not quite ready for you to do that. One of the things I want to have happen is everybody they have to go to their regular Telebear sections on Friday, by the way. This is the one and only week you'll do that. And you maybe can meet up with people in that section as a way of finding folks if you don't have a group. But just remember that all members of your group have to be in the same section. All right, and I will also discourage too much, strongly discourage 3-person groups. Okay, I know that sometimes people want to do that. Usually the 3-person groups are because we had a 4-person group that has one less person by the end of the term, and that tends to be tricky. So we're not going to start out that way. So try to shoot for 4 or 5-person groups. Okay, next Monday we'll actually turn on the registration process and let you do that. And then sometime next Wednesday or Thursday, we hopefully will know what your final sections are. Now that's an optimistic scenario. The pessimistic scenario might be that there's no way to schedule you all and we'll have to move one of the sections. That's happened, but that's a nuclear option that is a lot harder to deal with, and hopefully that won't happen. So try really hard to give us 2 possibles for your sections. Really hard. To the point that if you can't do that, I'm going to have you guys send me email with a nice explanation of why you can't come up with 2 sections. Okay? And that's just to try to avoid the nuclear option. And again, Friday, that's this Friday, go to your Telebear section. Okay? Or if you don't know what your Telebear section is, go to somebody else. But I'd prefer you go to the Telebears because that'll avoid swarming the TAs too much. There will be actual information at the sections this week. So, okay, any questions on this? Yeah.
If you're on the wait list and you get into a group, will that help your chances of getting into class or allow you to stay longer?
Yeah, probably not. I don't know what to tell people on the wait list. I mean, maybe you get a group with people on the wait list. I'm not sure what to tell you. That's tricky. If you're really high on the wait list, then maybe you could form a group. Okay. Any other questions? You know, I have to say this is the first term I've ever actually had to potentially kick people out. I'm hoping that I don't, but I think I may have to. Usually I let everybody in. But I don't know what the deal is about this term. I guess everybody's really optimistic. Yes?
Since I'm on the bottom of the wait list, will you know when you'll be kicking those people out or not?
Yeah, we'll have to make probably a decision by very, very early next week. Okay. So, now what we'll do is we'll talk for a little bit more, and then I'll actually give you guys a real break. So let's talk about phase 2, which I would call it here, which is hardware is getting cheaper, humans are now expensive. Okay, so this is a new mode. And basically, you can buy a computer for a few $1,000s as opposed to millions of dollars. That's kind of interesting. Operating systems technology is finally maturing in this time frame. And what's going on here but interactive time sharing? So the idea here is you use really cheap terminals, and we're talking about VT100 terminals or something that actually put text on the screen, to let multiple users use a computer. So we're going to take a resource that's potentially expensive, and we're going to make it even cheaper by putting a couple of terminals together and talking to it. Okay? So now the cost per human is much lower. Okay? And we're actually going to be willing, since computers are not so expensive anymore, to sacrifice CPU time to make humans happier. So this is interesting, right? It's now we can start trading CPU time for response time. And this is going to be a whole topic on scheduling. Okay? And you can start to see, by the way, where we go with this. How many people have gone to a website and it's not there in a second and you're just so annoyed you go in? Okay, there are, I've actually heard about companies that will remain nameless that do web search and that have done experiments where they've selectively tried slowing down the response time of people in certain areas and what they, of the country or whatever. And what they found is that when you selectively slow down past a certain point, not only do people get annoyed and go away during that session, they don't come back for months. Okay, so response time actually is very important to people. Okay, and what's interesting about sacrificing CPU time is we might actually let the user use CPU time to, heaven forbid, do things like debugging their program or editing it online. Okay, now these are all things that you take for granted, but nobody did this in the early days. It was too wasteful. Of course, an interesting problem with this is what I'll call the thrashing problem. You've got multiple people all trying to use the same resource, and the performance becomes nonlinear with number of users. So instead of, as users grow, slowing down with some steady pace, what actually happens is this response time actually becomes kind of almost like an exponential growth at some point, to where there's some number of users beyond which this thing is almost vertical. Okay? Why is that? Well, swapping I put down here as one option. We'll talk more about that later. But actually, in reality, this is a queuing effect. Okay? And pretty much your engineers, I take that as for granted, and every engineer should know that you never ever run a resource at 100%. Okay, what do I mean by that? Well, you build a bridge for exactly 1 ton. You never run a 1-ton truck over it, right? That's probably a bad idea. Okay, in computer speak, if you have so many CPU cycles and you use 100% of them, all of your individual users, because of queuing time, are going to see a ridiculous response time. They're going to be unhappy. So the real point to operate is more like 80% or something. And this is an important enough concept that we'll actually talk about queuing theory at the end of the term a little bit to give you an introduction to that. Okay? So also happening at the same time, are there any questions on that? Anybody actually seen this kind of response curve on? You see it everywhere. Once you know to look for it, you'll see it everywhere. Okay? The hamburger line at McDonald's has a response curve like this. All right. There was somebody question, or people have just seen this? Okay? All right. Now, the ARPANET was also happening about the same time, so you, as the internet-connected generation, ought to look at this time frame and think about this, because there was no internet at all before this. And there were several people working on this idea. One person at RAND Corporation, Barron, was interested in networks that would survive something like a nuclear disaster. That was just, he was thinking about that. You know, they tend to work with the Defense Department, and his ideas were you take what you're sending, you chop it into little pieces, and you send it on different paths so that if one of the paths is dead for some reason, you can get there on a different path. So that was how he came up with packet switching. Well, amusingly enough, other folks also were doing that. So the BBN team there was a BBN team also thinking about this, and they essentially came up with what was called the ARPANET, which was a research network set up for sending packets around. And it sort of started about in 1969 with the first node at UCLA. Okay? And by December, there were four nodes, and they're connected by 56 kilobit connections. Okay? 1971, on this very simple system, I'll show you a slightly bigger network in a moment, we got the first email. The 1970s, pretty much through all the 70s, there were less than 100 computers on the whole net. Okay? How many are there today? Hundreds of millions of them, right? More? Okay. So this is a little smaller now, right? So here's a picture of the ARPANET, actually, by 1980. And it's still got some connections to all of these places that you're used to. Okay, you know, you might imagine Harvard and you might imagine Stanford and a few others, but there are some places in the middle of the country which you would just never have expected as being on the main network, and these are where the supercomputer centers are and a few others. Kind of interesting, okay? There's no network to Europe at this time, okay? Well, I should take that back. There are networks to Europe, but certainly not with this level of connectivity. Okay. So let's put that aside for a second. We'll come back to the internet before we end this hour. But phase 3 is kind of where hardware is cheap and humans are extremely expensive. Okay? Now, computers are maybe $1,000. Programmer might be $100K a year. So if you can make somebody happy, give them a computer. Or maybe this is better. If you can make them more productive, give them a computer. Okay? And the idea of personal computing showed up. Okay? Surprisingly, before the early 80s, a personal computer was kind of not really had by very many people. Now, of course, these personal computers were limited initially. So we had things like MS-DOS, which we talked briefly about last time, where the operating system's essentially a big subroutine library. So it's not very sophisticated yet, but by gosh, I've got my own operating system and hardware running in my house. Okay, that was a big deal. And eventually, of course, the PCs become powerful, and operating systems have all the complexity of big operating systems again. Okay, and so by the time we got to Windows NT and OS/2 and some of those, we were redeveloping the same complexity that went into Multics and Unix and some of those. Okay, so it's kind of interesting that as the PCs went on this curve of more and more power, the operating system got more and more complicated. Okay, it's almost the disease of complexity. If you can make it more complicated, you will. Murphy's Law of Complexity. Huh, that sounds good. So here's an interesting question, though. Suppose we go the other direction. This is just a thought-provoking thing. So that computers are so cheap that we have little tiny, I don't know, computers in a cubic millimeter, for instance, which some of the faculty around here talk about, and they're everywhere. Can you get by without an operating system? Okay, because everything is so simple that you've got zillions of these things, but each one is very simple. Do you still need an operating system on them? This is like the ultimate PC idea. Microsoft probably wouldn't want that to happen, right? They'd want to have an operating system on everyone. What do you think? How many people think that you could make hardware cheap enough that you'd never need an operating system? Okay. Seems a little unlikely given the advantages I'm plugging for operating systems, right? Maybe they need to be better designed and simpler, but whether they ever go away is hard to say. Okay, so the other interesting thing we'll talk about before we take a break here is graphical user interfaces really came to the fore about this. And of course, you know that 160, how many people have ever taken 160 here? Anybody? That's a class on how do computers interact with users. Okay, this all started in the 80s. Xerox built the Xerox Star in 1981, and this was, believe it or not, the first machine that had mice and windows. Okay, it wasn't developed by Microsoft, wasn't developed by Apple, it was developed by Xerox at Xerox PARC. Okay, and this was their experiment in how to interact with users. This looks like it's got a lot of the stuff we're all used to, right? There seem to be icons here. There are windows. They overlap with each other. All right? And of course, in the early 80s, 1984, we had things like the Apple Lisa and the Macintosh. Anybody seen one of those old Macintoshes, the squarish things, right? Okay. So Xerox did it first. Apple did it afterwards. Who was the original innovator here? Okay, Xerox. Interestingly enough, Apple went on to sue Microsoft for using overlapping windows. because they were stealing the look and feel of Apple's Macintosh. Okay, now this is called the look and feel suit of 1988, and it's a very interesting take. Okay, especially since Apple got their ideas from Xerox. So, fortunately, Apple lost on this one. This is, by the way, I'm a big fan of Apple as a company, but this is one case where I'm very glad they lost, because if they had won on something has the same look and feel as my product, that would have put a lot of a damper on the software industry. You can imagine, right? It would have been pretty bad. And of course, Microsoft Windows looked a lot like the original Xerox version. This is, I think this is 3.1 version, so this is pretty old, still ran on top of DOS. There was no protection, so to speak, in this. Windows 95 claimed it had protection, but you could still easily load device drivers and stuff that would crash the machine. By Windows NT, this was pretty much a real operating system with actual protection, just like Multics. And then by the time we get to Windows 2000 and Windows XP and Windows Vista and 7 and all that sort of stuff, these are pretty much full operating systems. Okay, I should have put Windows 7 in here. I apologize, I didn't do that. Okay, questions? Yeah?
Where does X window come into play?
So X was going on along around the same time. The version of X Windows that really kind of was particularly good was kind of X11, and that was sort of in the late 90 time frame, or no, excuse me, late 89, early 90 time frame. So it's about the same time frame, but X was a little bit after the Macintosh, but right around the look and feel suit. So they were kind of going on in a stealthy fashion afterwards. Yeah. So HAL stands for hardware abstraction layer, and if you put a hardware abstraction layer in, you actually put some device-dependent software that makes all operating systems that run on top think they have the same hardware, and then you adjust the HAL for different hardware. And so it's a way of making Windows NT extremely portable. The problem is there is some inefficiencies to that, so by removing it, it's no longer portable, so these only run on pretty much x86, but you get more efficiency. So, okay, good. All right, I think, yes, so let's take a brief break, let's take about 4 minutes or 5 minutes, 4 minutes, and then come back and we'll continue. All right. Let's start relaxing. Thank you. Sure. Okay, so let's talk the last two phases here, everybody. So basically, I would say the modern distributed computing age kind of happened in the late 80s. And this is when the concepts of having clients separate from servers across the network really became common. All right, and that's when networking is as important as the compute. Okay, think about this. Up till now, we've been talking about the computer fills a room and we bow to the computer. Then the computer is smaller and we aren't quite as annoyed with the computer. And then the computer is small enough we can put it in our house. These are all about the computer, right? But starting about 1988 or so, it was really about the network. And we all take this for granted, but I mentioned earlier that I was actually on Project Athena, where it was not obvious that we could have clients, come on in, that are all identical, and your files are stored on the server, and so your unique identity is remote. Okay, that was actually kind of revolutionary at the time. And you know, what kind of services can you get, come on in, remotely are things like computing and file storage, whatever. Okay. Now, of course, during this time, this was really the rise of the internet, and of course, you remember the ARPANET was this research project, and it turned out that originally the ARPANET, actually these IMPs for Internet Message Processors, that's not the right thing, I forget what the I stands for, were basically 256 addresses. Okay, so 1 byte. All right, so you basically can't put a lot of nodes on the ARPANET. Okay, and so this is the point at which things really started getting big. And the internet in its final form was a combination of research at universities and actually work in industry. Berkeley had a big part to do with the internet because of Berkeley Unix. Okay, in fact, BSD 4.2, which had the new sockets interface and the better TCP/IP from Jacobson and a bunch of this stuff, was so important to the world that people were actually, they had runners waiting to grab the tapes for the release when it was put out so they could run them to their companies. Okay, so that actually was Berkeley. That was here. And basically, the internet was kind of the basis on which a lot of other standards happened. And so what are some services provided by the internet? Well, you know, shared access to computing resources was through Telnet in the 70s. Shared access to data and files were things like FTP, NFS, AFS. That's in the 80s. Instant messaging in the 90s. Audio and video in the 90s and early noughties, as a friend of mine calls this. And it's things, things like www, all that sort of stuff for information dissemination all across the net. Okay? So the ARPANET really evolved into the internet. And of course, we have the very most important thing was the first spam message. And I actually not sure how they're sure this was the first one, but 1st of May 1978. I'm not sure what it said. I should really find that out. TCP/IP, which is the protocol of the internet pretty much today. There were a few early ones, but this is the one that won out, was in the early 80s, where it really became stable. Things like DNS and so on. We also had this split between the public and the military nets. So now Milnet is actually a completely separate network with gateways between. You can imagine why you might want to do that. In the middle 80s, the National Science Foundation actually built the NSFNet, which was a network backbone to try to increase the amount of traffic for research. Okay, and it was linking supercomputer centers, and it was about 1.5 megabits per second. In the early or the late 80s, basically we had a bunch of regional networks that all got linked together. And so as you're imagining here, what's happening is people are adding more and more capabilities, and it's kind of done in a haphazard fashion. It's not like someone sat down and said, I'm going to design the ideal internet. What happened instead was they put a link from here to here, and a link from there to there, and a link from there to there, and they connected them all together with this protocol that mostly works most of the time. We'll talk about that toward the end of the term. And you get the internet. Okay? So what is a communication network? We'll talk a lot about this as toward the end of the term. But the network offers a very basic service, move information. So you can do that with birds. You can do that with a fire, right? You have on a mountain. You can do it with messengers and trucks and telegraphs and telephones. The internet is just another way to move information. Okay? So what distinguishes different types of networks? The services they provide. So, for instance, a bird has this unfortunate property that, well, you know, it doesn't necessarily work all the time. It's a little inconvenient to keep a bunch of them in a cage next to where you're sending messages, etc., right? So what distinguishes the services? Things like latency, bandwidth, loss rate, number of systems you can get to, service interface, reliability, all that sort of stuff. How many people have heard of the world's highest bandwidth network? SneakerNet. What is that? Yes?
You pick up a hard drive and you ship it.
That's right. You ship a bunch of hard drives to a remote location, and you just have had the highest bandwidth you could possibly achieve, because it would probably take you forever to transmit that over the network. It's called SneakerNet. Okay. That's a network. Okay? It's a little limited, but it's a network. So the infrastructure-centric view of networks, which is when you get into designing them, is about what communication medium are you using? Electrons, photons, what are the components, like links to carry bits from one point to another, interfaces to attach devices to links, switches to switch things, hosts are the things you're connecting, and so on. And we'll talk a lot more about this as the term goes on. But, and then, of course, you've got protocols on these networks. TCP/IP is just one protocol for sending information. Okay, so this idea, you start with, I want to get information from point A to point B, and then you successfully refine your design until you get to something that's extremely useful. And that's where networking comes into play. All of this was basically coming to the fore in the late 80s. Okay? Here's some network components. Links are things like fibers, interfaces are cards, switches look like this, big boxes. So what are some types of networks? Of course, we have local area networks, LANs, metropolitan area networks, MANs, you probably haven't heard of that much, wide area networks, WANs. And basically they're distinguished by what they carry. Okay, we'll talk more about that later. An interesting concept these days is the cloud. Okay, and where did that come from? Well, it came from the fact that people would draw a network as a cloud and say, oh, these guys are connected to it, because they didn't really care about the internals of how messages got from one point to another. It's in a cloud here. Okay? And of course, that became terminology for, well, now I've got subclouds. Okay? Now I can connect clouds with backbones. And I can talk about services that are out there in the cloud. Okay? Now you start hearing this modern terminology about everything's in the cloud. The problem is, of course, if you put 5 people who are in cloud computing in the same room and you ask them what the cloud is, they'll all give you 5 different answers. Okay? There's computers in the cloud and so on. Okay. So let's do a few other pieces of history. So 1988 was a great year for lots of things. It was also the year for the Morris internet worm. This was the granddaddy of all worms. It was the first self-reproducing worm that was sent off by a graduate student from Cornell. First-year graduate student. He thought it would be cool. Unfortunately, it actually ground most of the existing internet to a halt for a week. Okay, we're talking businesses shut down, email got nowhere. And the basic idea was that it was launched close of workday November 2nd, and by the next day it was just game over for lots of people. Consumed resources to the point bringing down infected machines. So here was the idea. I'm going to come up with vectors into the machine. So there are several ways that he broke in. Once you get there, it downloads itself, and then it talks to other machines. What he didn't account, and all he wanted to do was put the program on every machine and be able to say, oh, look what I did. This is cool. The problem is that it over-reproduced so that machines would have hundreds or thousands of copies all simultaneously running. Okay, so he kind of screwed up there. And, you know, so there was a whole bunch of ways of getting in. They would do look at local files where people kept their passwords and use that to get in. There were some bugs in the finger daemon. There was a debug command that they could use to break in. There was a way to break in with sendmail. Oh, excuse me. The finger attack was actually a Stack Overflow bug. The sendmail attack was a debug command. But these were different ways of getting in. And then once a little program got in there, it would download the rest of itself, and then the worm would go through the password file and try to find passwords it could decrypt with a dictionary attack, and then it would talk to other people and so on and so forth. And yeah, it was clever. Not sure it was the right thing to have done at the time. Now, unfortunately, does anybody know what happened to Morris? Okay, well, let's say what first happened to Morris is he actually got arrested and he had a felony conviction for computer hacking, and now he's a professor at MIT. Yeah. So anyway, I'm not sure that you want to have that way of getting to become a professor at MIT. I think there are much better ways to do it. He has trouble getting on airplanes now because of the felony conviction. So 2000 was one of the first PC viruses that really went all over the place. There were many of them before, but the love letter virus, basically you got an email that said, please, check the attached, and then you'd click on it, and it would be a virtual basic script that would download and infect your machine, and it would email itself to everyone in your Outlook address book. It would replace files on your computer, download passwords, and so on, and crack them. And this had actually 60 to 80% of U.S. companies were infected at one point. Okay, so, and obviously our system here was almost infected. So, yeah. So as you can see, once we reached 2000, now suddenly we're in the mega mode of viruses. Okay, now that's not to say there weren't lots of viruses prior to that, but these were really taken off. So finally, phase 5 in our little story here. Is really where the network is so central that the devices are kind of disposable. Okay, and not to say that we don't all love our cell phones, but in some sense, if you lost or destroyed your cell phone, you could get another one. Right? It's really the network it's attached to that matters. Right? It's the services for phone. It's the services for the web. It's the services for your picture storage. All of that stuff that's important, not the device. And so that's why we would say devices are ubiquitous. We have wireless everywhere, wide area networking everywhere, okay? Heck, now 3G, 4G, all of these different technologies will make cell phone networking very fast, okay? And it's kind of interesting that traditionally you think of a computer, it's got a mouse and a monitor and keyboards and so on. Basically, and a CPU. Basically, what we've done is we've split all those pieces apart, so the display is in one place and the keyboard's in another, and so on, right? So you could imagine your phone, you're typing on this and something's showing up on a display or something. Okay, that's fine, right? Because it's the network that matters, okay? And of course, 2000s were also peer-to-peer systems. That was what I did a bunch of research in a decade ago, and that's where we had people sharing files. I won't say stealing files. There was a lot of other interesting uses for peer-to-peer. We'll talk about peer-to-peer later in the term because it's an interesting rethinking of systems. And of course, you saw this picture yesterday, but this idea that everything's connected and there's lots of these things, services in the background that are used by all your devices, is it's just the way it is today. You've grown up with it, so it doesn't even seem weird to you guys, probably, right? It's just the way you're used to. And this is sort of the Citrus model. Was this, you know about the Center for Information Technology Research in the Interest of Society. That's the new building next door. Their view kind of is the network is the operating system. Okay. And of course, there's another view, which, if you think about it, what's in the network? Well, the data centers are some of the things in the network, and so now rather than the computer being a single device, the computer is a data center, right? So Google, you go to do a search. Does that search go to one particular machine? No. It goes to a data center, and it kind of floats around until the right answer comes back at you, right? There's no one computer you're actually connecting to there. Okay, and we actually had an interesting talk a few years ago about, basically how this data center is running these programs, which are things like web search and Gmail, but running the program is a very diffuse thing in this modern world. Okay. So we have these warehouse-sized machines backing our little tiny cell phones. So here's a diagram from your book, which is kind of interesting. So if you think of mainframes as these big computers that filled rooms, and in the beginning, they had no software. They had some guy standing in front of a patch board. Remember that? And then eventually they got compilers and batch computing and operating systems. And he got to Multics, which was kind of the creme de la creme of operating systems. And then you've got mini computers, which were little things that kind of fit under your desk. And then you've got desktop computers and then handheld computers. And what's kind of interesting is as each of these lines progressed in powerfulness, the ideas of the top kind of filtered their way down. So Unix was kind of the Multics for mini computers. And as you get down to desktop computers, you've got Windows NT as kind of the Multics for mini computers. And you get down to here, I don't know, maybe this is Android or something, hard to say. That's not quite that level of sophistication yet. But this idea that the concepts from the more complicated things eventually filter down is what happens. Okay. So just a brief summary, what we said here is change happens all the time. You don't think about this as, look how stupid batch processing was, but rather, yeah, it made sense at the time. Situation today is much like the late 80s. A large operating system's 10 million lines of code, 5 million for a browser, okay? Complexity. Complexity reigns. So that's kind of why this class is here. Okay, I'm going to take the final couple minutes of the class and give you a really quick tour of a couple of things about the OS, and then we'll obviously hit on these later. But this is your relaxing toward the end sort of view. So what are some pieces of the operating system? So process management, main memory management, I/O system management, file management, networking. Okay, these are all things that we could talk about, and we will. What does the OS do? So services that might be there, things like, well, program execution. There needs to be components that figure out what instructions to execute together to give you a program. There might need to be things that figure out how to do I/O. Okay, we have, I can use my file browser to both talk to my hard disk drive, talk to a network file system, and talk to a little USB key, and I don't have to know that those are very different devices. Why is that? The operating system's there hiding that detail for me. Okay? File system manipulation are things that have to happen. So we'll talk about the file system. Networking. Remember, the network is the operating system. So clearly that has to be done by the OS. Other things like error detection, resource allocation, accounting. Okay, these maybe are less exciting, but they're all things that you could imagine happen. Protection. Talked about that at the beginning. What's the API with the operating system? Well, the system call interface. I briefly mentioned that earlier, but user applications have library calls that call into the kernel. Those are the system calls. Okay, so the operating system has a set of interfaces that you get to use. Okay, you could look at Chapter 2 of the 7th edition. What's the structure of your operating system? Well, it could be one level of code like MS-DOS, or two levels of code like Unix, right, kernel system. It could be layered, okay, many layers. It could be a microkernel. This is a case where you take all those components I showed you earlier, file system, network, all of those things, and you actually make them processes running in their own address space, protected from each other with a microkernel in the middle. I'm just throwing these terms out to you. But the point of that is that then different parts of the operating system can't mess each other up because they don't have the same mapping to physical memory. Okay, so these are all ways of building things. Modular, this is kind of a Linux structure. Okay, so we could spend a bunch of time, and we'll spend some time over the course of the term, talking about the structure. How do we organize our operating systems in a way to make them understandable? And these, by the way, are all techniques for eliminating complexity. All right? I don't know if people have hit this onto you hard enough as you've been going through school here, but you get rid of complexity by managing it. Layering, abstraction, whatever. Okay? So here is MS-DOS. That's the simplest structure. No protection. All the OS is a library. Here's Unix, is also kind of simple. 2 levels. Kernel user. Problem with that is if the kernel screws up, it crashes itself. Here, see, all of these things are in the same level of priority and therefore can screw each other up. So if you have bugs in your kernel, over on one side, it crashes the other. Here's a layered structure. That's kind of boring, but you got layer 0 like the HAL, followed by another layer, followed by another layer, by another layer. Okay, there's layering. Here's microkernel. Okay, and basically this was the idea that you move a bunch of that stuff all into user space with different address spaces, and therefore it can't screw each other up. Okay, I think that's all I want to talk about structure for now. But in conclusion, we talked about how a very rapid change in the hardware leads to changes in the OS. You could basically see that complexity creeping in. We went from batch to multi-programming to time sharing to graphic interfaces to ubiquitous devices to, cyberspace. Where are we now? OS features migrated from mainframes down. Standard components are things like process control, main memory, I/O, file systems, user interfaces. And finally, the one thing you take away from today is policy versus mechanism. We've been talking a lot about mechanisms. The question will be how to use them to get the policies we want. All right, have a great weekend. Form your groups. Don't forget, Friday, you go to your Telebears section.